So the cycles aren't disjoint. Our goal is to get disjoint cycles. So as we start looking at this, let's start with 1 and see, well, where does 1 go? Now, anytime we're working with permutations, it's function composition. So we start from the right and we work our way left. The rightmost function is what's done first, then the next one, then the next one. It's one of the few times we actually go right to left. Most of the time we're very familiar going left to right, but the right to left with function composition. So 1 goes to 2. Then 2 goes to 3, and 3 is unchanged. So we apply, we follow it through. 1 goes to 2, we've applied that permutation for 1. Then where does 2 go? It goes to 3. 3 is unchanged. So ultimately 1 goes to 3. Then we can figure, okay, well, where does 3 go? Because in the cycle notation, 1 goes to 3, we need to know where 3 goes. So let's see, 3 goes to 1, which isn't changed, which goes to 4. So then we figure, okay, where does 4 go? Where does 4 go?
4 goes to 9. I think 4 just goes to 9.
I like the way you said that. Yeah. 4 goes to 9, and 9 doesn't move, so 4 just goes to 9. All right, so 9 then goes to 3, gets sent on to 4, gets sent to 8. Where does 8 go? Nowhere, nowhere to 6. Where does 6 go? Nowhere, nowhere to 1, which closes off this cycle. 6 then goes back to 1. Now, there are some numbers appearing here, so we at least need to double check. Are they changed in the course? So we don't know where 2 is going yet. So let's see, 2 goes to 4, which goes to 5 and stays there. So 2 goes to 5. 5 is unchanged, goes to 2, stays there. So ultimately 5 goes to 2. And let's see, are there anything else we're missing? 1, 2, 3. 7. Well, none of these did anything to 7 in the first place. The composition still. 7 goes to 7. We could write that down. Typically we don't. About the only time we write down that portion of a permutation is when it's the identity. We've got to write something down to indicate it's the identity. We can't just leave them all off and leave it blank. And one disadvantage the cycle notation has, we know we're at least in S9. We might be in S10, S11, S12, don't know. In a sense, don't really care. We know where 1 through 9 goes, that's enough. And these now are disjoint because 2 and 5 are in here, but they're not in here. None of these are in there. And once we have the disjoint cycles, disjoint cycles are commutative. These would not be. If we rearrange the order of these, we'd get a different product. But when they're disjoint, since this is the only one that changes 2 and 5, and this is the only one that changes the others, doesn't matter if we change 2 and 5 first and then nothing, or do nothing and then do 2 and 5, it's not going to matter. And for that matter, whether we say 2-5 or 5-2, same thing. And say here, this also has lots of other names. We could call it 4-9, 8-6, 1-3. So it's the same thing. 4 goes to 9, which goes to 8, which goes to 6, which goes to 1, which goes to 3, which goes to 4. So there's not necessarily, I mean, it's the same cycle, even though our first look at it, thinking, it doesn't look the same. Once we understand the cycle notation, we should realize, oh, it is the same. It's just telling us where each element goes. And if we don't see it, it's not changed at all. I think that addresses the other question I had.
That would be your answer.
Yeah, this would be the final answer, and this actually probably would put 7. or one form of the final answer. There are lots of other forms it could be. Other questions? Okay. Other questions from the homework in general that you've got, because that's due Tuesday. I mean, I'll take it Monday, but I want to have another opportunity Monday. If you get it to me Tuesday, I should be able to get it graded and give it back on Wednesday for us to talk about. The exam then is next Friday. Okay, well, we were working with cyclic groups then, the order of an element, and trying to kind of discover if the group is cyclic, what kind of things do we know about all the subgroups? And we've done examples mainly just with Zn under addition, where one generates, but I was trying to move away from that a little bit. But any kind of questions yet on what we've done so far with cyclic groups? Okay.
Can you just like read number 3, I guess?
But make sure it really says what I thought it was saying.
Well, I just don't understand. I guess I don't really understand how to read that. So do we have a function again, or?
Yeah, well, so on number 3, I'm defining a mapping. I'm sending A to A squared. And the question is, if we're going from the group of positive reals under multiplication to the same group, is it an isomorphism? So we have two groups, or the same group filling two roles, and a mapping. The question is, does it meet the criteria to be an isomorphism? Is it one-to-one? Is it onto? Does it preserve the operation? I mean, in one sense, every group is isomorphic to itself. Just don't do anything in the mapping. It's one-to-one. I mean, the identity mapping is one-to-one onto. It preserves the operation because it's not really doing anything. So typically, as we think of a group to itself, our interest would be, are there some other things that could work as isomorphisms? And so here's a candidate. If we square every element, does that work for being an isomorphism? And so we're going to go through the properties and decide, does it meet all the properties?
Could you kind of maybe elaborate on what onto is, and like, what onto and what the one are?
Okay. Well, let's see.
Just get it a little twisted in my head. when I start thinking about it.
So one-to-one, each output is different. So a couple ways we've described this. If x1 doesn't equal x2, then the outputs aren't equal as well. But usually if we're more abstract, not equal is hard to get a grip on. So typically we would look at the contrapositive of this that says if we somehow have ended up at the same place, well, the only way that's possible is if we in fact started at the same place. If two outputs happen to be equal, if we can prove whenever two outputs are equal, the inputs had to be equal, that's what it would take to show that it's one-to-one. Whereas onto is we get each output. have a mapping from A to B for any element in the potential outputs, there exists an element in A with f of A equal to B. For every possible output, we can figure out where it came from. So in a sense, they both have to deal with outputs. Onto is, do we get all possible outputs? One-to-one is, do we only get our outputs once? We're not concerned if we get all the possible outputs, but we're concerned, do we just get the outputs once? Or are there some repeats in the outputs? Be another way maybe to think of it. No output is repeated, every output is obtained. But with one-to-one, we don't have to get every possible output. Just the outputs that we do get, we need to make sure we get them only once. If we miss some outputs, that doesn't mess up one-to-one. It definitely messes up onto. That's the idea of onto. We get all the possible outputs. So if we miss one, the mapping's not onto. If we repeat any of them, the mapping's not one-to-one. And in fact, sometimes students even can confuse this just with the idea of a mapping. The idea of a mapping is each input is sent to exactly one output. So things like, well, in a table, 1, 3, 1, 4 isn't a mapping at all because we've got an input that's repeated. So we're not. For both of these, we're assuming we've already addressed that question. We really have a mapping. Each input is only going to one output. The question is, do we get all the outputs? Yes or no? If we get all the outputs, it's onto. Do we repeat any of the outputs that we get? If we repeat any of them, it's not one-to-one. If we don't repeat any of the outputs we get, then it is one-to-one. Yes?
So one-to-one, no repeats, correct?
No repeats in the outputs we get, yes.
In the output. And onto is all possible outputs.
We get them all, yeah.
Okay, my question is for, I don't know if it's confusing in my mind, do you know an easy way to remember, okay, one-to-one, that to not get them mixed up, one-to-one's the repeats, onto is the all possibles? Because in my mind, sometimes I get one-to-one and onto reversed in my head.
Okay. I don't know. Anybody else struggle with that and have a good suggestion as to how to not get the two ideas mixed up?
Wouldn't a graph do it? Horizontal, vertical line. If there's no repeats on a horizontal line, you get every.
Okay. So if we think in, so yeah, in terms of a graph, for one-to-one, we cross at most once. And onto, we cross at least once. Although I don't know if that still is helping kind of address what you're thinking of, how to not get the two confused. I mean, it is another way, I think, to help think of what does each one mean. One-to-one, if we cross more than once, there's a repeated output. If we don't cross, then there's an output we don't have. But in terms of how to keep them straight,
Think about a table of numbers and you have the inputs on one side and outputs on the other, and each input is mapped to only one output. So if you had 1, 2, 3 as your inputs and 1, 2, and 3 as your outputs, it will.
Because like 1, 2, 1, since it's 1, you can only map it to 1.
And 1 can only go to 1, 2 can't go to 1. It has to go to another number.
okay. Yeah, so
What did,
and part of what may may be confusing a little bit. If we're talking finite sets of the same size, you can't have one without the other. I mean, we'll go back to your 1, 2, 3. If we get different outputs, we're going to have to get them all. There's no way they can all be different if we don't use them all, if the sets are the same size. So when we're talking sets of the same size, which we certainly have been with permutations, 1 to 1 and on to happen at the same time. But if the sets are different sizes, or not finite, then you could get one without the other. You could repeat everything and still get all the possible outputs. You cannot repeat anything and still miss some possible outputs. So, I don't know. I guess for me, I'm thinking in terms of onto, sort of covering the outputs, that they're all covered. That the mapping is onto, we get them all.
Okay. As I say, if I could just remember one, because there's only two.
Yeah, right, yeah, and if you can remember one, the other one's the other one.
And I just, one more question for them. Am I really the only person that gets confused in that?
No.
Okay, thank you. I felt, wow, I'm pretty bad.
Back for our permutations, it's the transposition idea. Yeah, you get 1 and 2 mixed up and it's flip them.
So when you say all the outputs, do you mean all of them in the set, or what, like,
Yes.
what is considered all?
Wherever we are mapping to, for any or for all, they actually come from somewhere.
So if we're in the set of real numbers, and you give us an equation, and it doesn't map to one of those real numbers, is it not onto?
Correct. So let's.
So I guess for an example, you did, in notes, you said from the real numbers to the real numbers, or the integers, I'm sorry, you said z to z,
Mm-hmm.
and then you gave like x squared. Is that is not onto, because it doesn't give us, like, you can't get one, or not one, you can't get like 3?
Correct. Yeah, f of x is never 3. There's no integer which when we square would give us 3.
You can't get negatives either, right?
And you can't get negatives. Yeah, there are all kinds of things we can't get here going z to z. So it's not onto. That there are things we don't cover in the outputs.
Is a square root of a number, that's not real, right? That's irrational, or is that real?
Depends on the number. I mean, no, the square root of 4,
Yeah.
the square root of 3 is irrational. So it depends on the number. I mean, so when we see the number, so as you're kind of thinking, there's a sense we can solve this if we use the square root of 3. And that's part of it too, is to realize the 1 to 1 and onto. It's part of what goes into the mapping is what sets are we being asked to work with. Because this particular mapping, under other circumstances, other sets, could be onto. If we're working with, say, the reals to the positive reals in 0, we get all the positive reals in 0 by using the square root. But if I'm only going integers to integers, there are lots of integers I don't get by squaring some other integer.
Whenever you have the positive reals, what was that multiplication sign for?
That meant the operation was multiplication,
In what way?
as opposed to addition.
But you have the set of all positive real numbers. I'm a bit confused.
If there's ever any uncertainty what operation we're using, We'll indicate what operation we're using. So in terms of reals, if I told you 2 star 3, you need to know what operation I'm using.
Yes.
If I'm adding, what is it?
It's, or the addition sign, you mean the.
No, just what number is it if I use addition?
Oh, 5.
Yeah, so it's 5 if the operation is addition. What is it if I'm using multiplication?
6.
6. There are other operations I could use as well, but if it is one of the standard ones, I will tell you. So the multiplication symbol means we are using, this is the group, under multiplication, as opposed to we're working with this set under addition, or under some other operation we could be working with.
So when you had the group of all positive reals under multiplication, and then group 2 was also that.
Mhm.
I suppose that's just saying you can't get any negative numbers, but you can, yeah, okay.
Well, in that sense, we needed to know the multiplication to check, like, when you have to do the f of a, f of b equals, like that, you need to know its multiplication for that.
Okay.
So like for the 1-to-1 onto, you don't necessarily need to know that it's multiplication.
That's true, yeah, the one-to-one and onto the operation
Then
doesn't
you
matter.
use that on the-
Yeah.
When we're preserving the operation, we have to know what the operation is if we're going to be preserving. And right now we've got 2 operations we're familiar with, addition and multiplication. We're moving toward familiarity with composition if we're talking permutations. If it's some other operation, they're going to have to tell us pretty specifically what that other operation is. But if it is the typical addition or multiplication, I will just indicate it's this group using the operation of addition or using the operation of multiplication. And we've done that with the reals, the integers. We've done it in ZN. Sometimes we talk addition, sometimes we talk multiplication. And so since in those sets we've talked both operations, I can't just say, look at this group. We need to know, what operation am I supposed to be looking at with this group? So I will tell you what operation are we looking at with the group. Okay. Other questions?
If you were to give us a set of real numbers, what would that look like? Just kind of a base.
What,
It's
give
not-
you the set of,
The set of real numbers, so like an R. Yes.
I'm not sure I'm understanding your
What
question.
is that? What is the set, I guess? What are the numbers in there? It's really like,
1, 2, pi, square root of 2,
so it's like anything rational.
no,
Anything
square root of
real?
2. The reals is all the numbers we've talked about. I mean, it's the integers, you add in the rationals, you add in the irrationals. Yeah, everything but complex numbers, yeah, the imaginary numbers. Or even beyond that. There are other numbers that people have created beyond the imaginaries. There are quaternions. There's some other numbers. In calculus, the real numbers are what are worth the most. I mean, I don't know. At what point do you hit real numbers? I mean,
Are real numbers all both positive and negative?
yes,
So it's pretty much everything except imaginary.
everything's except imaginary, yeah.
Oh, wow. Well,
Yeah. Well, I mean, if we think back in mathematical history, I mean, starting off, we started with the natural numbers. In fact, that's probably why they're called the natural numbers. They're sort of the natural place to start, 1, 2, 3, etc. At some point, someone decided, oh, you need 0 in there so that you can answer some questions. So we throw in 0, and those are the whole numbers. And then, well, we need some negatives. So we throw in the negatives, and we get the whole integers then. Negative 1, 2, 3. And then somebody decided, well, If we're multiplying, I need some inverses for multiplication. I don't have those, just among the integers. So we've got to throw in the rationals, all the fractions. Which doesn't throw out any of the integers. I mean, 2 can be written as a fraction. So kind of at each point, we're typically not throwing away any of the numbers we've had. We're adding to it and getting a bigger set, because the set we had actually was missing some things. And then we do that again. We don't have square roots among the rationals for a lot of the numbers, so we throw those square roots in, lots of other things we have to throw in. We get the real numbers then. Okay. I want to do a couple more things with cyclic groups to try to get more comfortable with the idea that if we can find a generator and know our group is cyclic, then that really tells us everything we need to know about the group. The generator and how it generates really describes everything. So let's jump to, say, this one. So we're going to do in Z13, the non-zero elements, or the elements that have a multiplicative inverse, which happens to be everything but 0. But we're going to be multiplying like we're on a 13-hour clock. So we've got 1, 2, 3, up to 12. So there are 12 elements in here. And I think the last time we decided what one element is not going to work as the generator. 1. Yeah, the identity will never work as the generator, because if we start with the identity combined with itself as the identity, it doesn't generate much. It always generates a subgroup with one element. It's not going to generate the whole thing. So we know that one's not going to work. Off the top of our head, my guess is we don't know which other ones may or may not work. So let's try, I don't know, let's try 2. So 2 times 2 is what? 4, 8, 16, otherwise known as 3, 6, 12, 24, otherwise known as 11. And I'm going to stop here. My claim would be, at this point, I know I'm going to get everything. Anybody? I heard somebody agree. So why do you think I know that at this point?
Because you've gone over halfway through the
I've gone over halfway through. Every cyclic subgroup is going to be of a size that divides 12. Once I know it's not of size 6, it's got to be of size 12. I mean, I could finish it up, and we will, but as we look for generators, we're either going to get back to the identity before we get to 12, or it'll go all the way to 12, but if we get to the identity before we get to 12, it will be in some multiple of 12, or some factor of 12 steps. So 2 steps, 3 steps, 4 steps, or 6 steps. Those are the only sizes of subgroups we can get out of this. So once I'm past 6, I know I'm going to get it all. So let's continue then. Let's see, 22, otherwise known as 9, 18, otherwise known as 5, 10, 20, otherwise known as 7, and then 14, otherwise known as 1. Now, another reason that's kind of handy is, suppose you make a mistake somewhere in here. At what point might you know that? Well, if you hit the identity, say, after 8 times, that's not supposed to happen. If it happened, somewhere you've got a mistake. Or if you hit it, say, after 5 times. Or if you hit a repeat and you haven't gone through one, somewhere there's a mistake. Because it's only supposed to repeat after you hit one and then cycle back through. So this group is cyclic. Once we know it's cyclic, we should know everything about this group. We should know the other generators. We should know how to generate subgroups of size 2, 3, 4, and 6.
How do we know it's cyclic? Because we got the generator.
Yeah, if we find an element that generates the whole thing, it's cyclic. We'll see if we can find an example maybe where we decide it's not cyclic, in which case it's far less predictable in what we can do with it. Because it's not going to meet this criteria. So as we think, other generators. Anybody spot another generator? 4. 4? Actually, I don't think 4 is. And the reason I don't think 4 is in position 2. 2 and 12 share a divisor. If it shares, if the position and the size of the group share a divisor, it's going to generate something less. In fact, what 4 will generate is a subgroup of 6 elements, because the divisor it shares is 2. So the subgroups of this size, so subgroups of size D are going to be generated by A to the M, where the greatest common divisor of M and N is D. Or, wait a minute, no. N divided by D. Now I'm having which way is it exactly? So the greatest common divisor of 2 and 12 is 2. It generates a subgroup of size 6. So I think what's kind of bothering me here is normally I've done the greatest common divisor is D, and the size is the other factor. So maybe in fact I should write the size times the greatest common divisor of the position, and N is always N. So position 2, the greatest common divisor of 2 and 12 is 2. It's going to generate a subgroup of size 6. What else is going to generate a subgroup of size 6? Is there another position who has the greatest common divisor of 2 with 12? 10. So that's 12. So the 10th position. Both of those, and we don't even have to check them. We probably will check just to make sure, but we don't even really have to check them since we are in position 2 and position 10. And I think it's purely coincidental here that 10 is in position 10. With the greatest common divisor of the position and 12 is 2, they are both going to generate a subgroup of size 6. So where are the other generators going to be? In what positions? What's the greatest common divisor have to be? If the size is going to be 12, what's the greatest common divisor going to have to be? 12 times what is going to give us 12? 1. So the first position, are there other positions where the greatest common divisor is 1? 11. 7. 1, 2, 3, 4, 5, 6, 7. There's one more, I think. 5. So the other generators here are 6, 11, and 7. In the positions where the greatest common divisor of the position and 12 equals 1. And we'll sometimes call this relatively prime.
Does the 2 not become 1? Is it
Well,
not
we already had the 2 as,
Oh, okay.
the 2 we'd already identified. We were looking, what are the other generators? So, yeah, this is all the generators. But in terms of deciding it's cyclic, we first have to kind of stumble on one. I don't know a good pattern for being sure we can find the first one. Other than just try something and either we're successful or we're not. And if we're not, then we know other things not to try. And we can try something else. But if we are successful, once we are successful and find a generator, we know everything that we're interested in knowing. And the things we're interested in, what other generators are there? What about all the subgroups? So for a subgroup of size 2, what position should I look in? For size of 2, what do I need this greatest common divisor to be? I'm going to get 12. Yeah, I need 6. What position has the greatest common divisor of 6 when we take that position in 12?
6.
6. 6 is the only one. And so here in the 6th position, and we probably may, well, I doubt we realize, it actually turns out that n minus 1 squared, or yeah, n minus 1 squared is always going to 1. In fact, that we can see algebraically. If we think of what n minus 1 quantity squared is, algebraically, what is that? Just usual algebra. N squared minus 2n plus 1. When we're looking on n-hour clocks, any multiple of n we can throw away. The n squared we can throw away, the minus 2n we can throw away. What are we going to be left with? It's always going to be 1. So it actually turns out that the n minus 1 always ends up in the middle position. And it's always what's going to generate a subgroup of size 2. Okay. For size 3, what positions do we need to look at? The 4th position. Is there another one? The 8th position. 5, 6, yeah, the 8th position. That one I think I'll do. Let's see. So 3 times 3 is 9, times 3 is 27, otherwise known as 1.
How can you do the 8th position? Because isn't 3 times 8 24, so that's a multiple of 12?
But what's the greatest common divisor of 8 and 12? So it's not the size times the position. It's the size times the greatest common divisor of the position and 12. When the position's small, those are the same. So like for 4, the greatest common divisor of 4 and 12 happens to be 4. But for 8, greatest common divisor of 8 and 12 is again 4. Just like 10 was as well. The greatest common divisor of 10 and 12 was 2, so it generated the same thing that the second position did, which was a subgroup of size 6. Okay, so everything here is generating something. Let's see. So for 4, the positions that, for size of 4, 4 times the greatest common divisor has to be 12. So that greatest common divisor has to be 3, which means what positions? What positions are going to have a greatest common divisor of 3? 9 and 3. I mean, and so we left, I mean, the third position and the 9th position both generate a subgroup of 4 elements. I'm going to pick the 5. 5 times 5 is 25, otherwise known as 12. Times 5 is 60, otherwise known as 8. Times 5 is 40, otherwise known as 1, because we're on the 13-hour clock. We're not used to a 13-hour clock, so we have to think a little bit about 60. 4 times around gets us to 52, there's 8 more. 40, 3 times around gets us 39, there's 1 more. And it's a little weird talking multiplication to think we're on a 13-hour clock, but since there's an odd number of hours, we never stop at 0. We still go around, but we never end up at 0 because of the odd number. There's no way, or excuse me, the prime number, not the odd, the prime number. There's no way with these numbers we would end up with a multiple of a prime. Whereas, say for 15, there are ways we can end up at a multiple of 15 using numbers we've got. Because 15 is not prime. So notice, we've got, once we can stumble on a generator, that tells us everything. It tells us what the other generators are. It tells us we will have exactly one subgroup of every size, and we can figure out exactly what the generators are. And we can describe everything about this once we stumble on one generator. In the case we want to check, I mean, say with 6. 6 is a generator. And notice, even in 6, the things that are in positions 1, 5, 7, and 11 are the same things that are in positions 1, 5, 7, and 11 with the other generator. Not necessarily in position 5 both places, but they're somewhere in the list. What was in position 6 in that one is in position 6 here. The position, say, 4 and 8, the 3 and the 9. Notice what's in position, put my mark on this, 4 and 8. Positions 3 and 9 were 8 and 5. Notice what's in positions 3 and 9 here. So as long as we can stumble with on a generator, we know everything. Okay. I want to do more, but I've only got 2 minutes. So, any other questions here? Because in 2 minutes I can't do what I want to do. So, I shouldn't say it that way because that makes it sound like I don't want to see if you've got any questions. Monday, I do hope to come back and pursue this a little bit because stumbling on this first generator it could be a challenge. And there's something that could happen while we're looking for that first generator that would also give us some information, even if it's not, oh, I found the generator. And so I definitely want to look at that, but that's going to take more than 2 minutes to talk about that. So I will see you Monday. And if you happen to come in a little late, don't just rush out. I'm trying to double check. All right, yes.
I understand you guys are London. I guess the Chris comes by in 12 is still one. How is that?
From our generator, so we're not
We're
looking,
looking at the position, not the actual number.
right, we're
Okay.
looking at the position.
And then the number that position leads to, that's the generator. Oh, okay.
Yes. And that's why I've switched and wanted to look at multiplication, because in multiplication, the fifth position isn't necessarily 5. I mean, the seventh position was not 7. 7 showed up in one of our positions.
Okay.
11 showed up in one
It
of the
just happens
positions.
that they
It
produce
just
each
happened,
other.
and it just happened, you know, the 10 was in the 10th position.
Yeah.
I mean, under addition, one generates the whole thing, and the number of the position are the same all the way through. They are always the same. So I wanted to look at some where the number of the position were not the same. So we are looking at the fifth position. It happens to be something other than 5.
Got it.
The number that it is what the generator is.
Sweet.
I'm hoping with the math office tomorrow, registration,
Registration's in the student union,
student union at 7:45.
7:45, yeah. We'll
Okay.
kind of make sure that things are presentable and get things set up and
Around
be
that.
ready when they come,
Okay.
so.
Just not sure, on question 1 here, it says, it's asking if F, are you just wondering about the F equation? Or
Yes.
are you wondering about this?
No, just the F.
Just the F?
Mhm.
All right, for sure.
Couple questions. Where are the graders meeting?
The graders are meeting in the, maybe the Success Center office area.
Okay, and then a question about this. Looking at this, it looks like the generators never end up in these subgroups. Is that always going to be the case? 6, 11,
Yes.
17, okay. So if we-
That is, because actually, the things that do end up in here will generate something smaller. So you, actually, done. Even in this one, notice what is in position 2. It's the same element that would generate, so looking at this then as a 4-element group. In position 2, there should be something that would generate a 2-element subgroup.
okay,
And it is the same. So yeah, the generator can't show up in here, because then the generator would generate something smaller than the whole group.
okay. So then that'll
So-
help you find generators.
That actually can help find generators as well, yeah, if you're,
If you find the wrong one a lot.
well, and what we'll see Monday, if as we look and we end up, say, with 2 cyclic subgroups of the same size, but they're not the same, then it can't be cyclic.
Okay.
Because if it really is cyclic, there's only one subgroup of size 4. So if we happen to be looking and happen to stumble on 2 subgroups that are both of size 4, but they are not the same subgroup, it cannot be a cyclic group. Because if it were cyclic, there would be only one of size 4.
Cool.
And if we find that there are 2, that would be enough. So we really don't have to try everything before we can make the conclusion, oh, this isn't going to be cyclic. We just have to try enough to realize either, oh, I found the generator, so it is, or I found some other problem that's like, oh, it's not, because if it were cyclic, it wouldn't have this problem. And since it has this problem, it can't be cyclic.
All right.
But yeah, you're definitely right that as we do this, the generator's not going to show up in any of these subgroups. Because anything that shows up in a subgroup would generate a subgroup of this. So there's no way it could be generating the whole thing if these generate a subgroup of this group. So I mean, like 8 and 5 here generate the same thing. Well, just looking here, notice 8's in the 3rd position. What's in the 3rd position of a 4-element group would generate the same 4-element group. We didn't observe that from here. We observed it from back in the original, but it still holds true looking at the smaller set as a 4-element subgroup, what's in position 3 should generate it as well, and it does.
Alright,
I had a couple questions on the homework.
Okay.
These two. For permutation and D of the cyclic subgroup generated by that permutation, isn't that essentially the same as these, or am I misreading?
Well, I mean, when we talk about a cyclic subgroup, we are starting with an element and combining with itself again and again and again and again and again. And so, so in D, we came up with this. If we take that and combine it with itself and do it again and again and again and again, eventually we'll get to the identity. What do we end up with? How many elements are we going to have in that group?
It's still a bit confused. Something that's not working today for me.
So if we start with that, combine it with itself, we'll get another permutation.
Just
again.
one of these.
No, this is the permutation.
Okay.
Combine that with itself, we get another permutation. Do it again, we get another permutation. Do it again, we get another permutation. If we do it long enough, eventually we will get the identity permutation, and we will have generated the subgroup that element generates. Kind of just like we did here. We took 2 and we combined it with itself. It was just easier here, because we're more familiar with multiplying. Take the number, combine it with itself. Do it again. Do it again, do it again, do it again, do it again, until you get the identity. We're going to do the same thing there.
So you would do this for, it's supposed to be much easier to use the,
I think the cycle notation is much easier. So we're starting in this case, I think so. So we've got what, 1, 7, 8.
how would you combine that with itself? 2, 4, 3, 5, 6.
So where's 1 going to go?
You just follow it through like you, there's 1, 7, 8.
1 goes to 8. Where's 8 going to go?
7.
Where's 7 go?
And that has to go to
Yeah, 7 goes to 8, back to 1. All right, so
These would just reorder those subgroups. Or not the subgroups, the notation.
so if we started with our alpha, which was just this, we're figuring out alpha squared. So where's 2 going to go? Where's 3 going to go? Actually, I've got to go. I'm sorry. It just occurred to me, I have a commitment at 9 that I have to be there for.
Oh, sorry.
So, yeah, I'm sorry as well, because I want to help, but